Mm.
Okay, so hello everyone, and welcome to the Conference of Gravity as an Effective Field Theory conducted by the National Science and Research Society of Nepal. So today it is a great honor actually to welcome one of the leading minds in theoretical physics, Professor Claudia de Rham. She is currently a faculty at the Imperial College London. She earned her PhD from the University of Cambridge and went on to hold many prestigious positions at institutions such as McGill University or Case Western Reserve University. And our groundbreaking research sits at the intersection of cosmology, high energy physics, where actually she has reshaped our understanding of gravity, a major fundamental force itself. And she is especially renowned for her work at the massive gravity. So she has like she has developed ghost free theories, and I think she will be getting in some of that with her on. So today she will guide us through a fascinating topic, which is gravity, the landscape of gravity, and which is one of the most elemental and I think the least understood fundamental forces of our nature. So please join me in very heartily welcoming our professor. So thank you, Professor, for agreeing to talk with us, and the stage is all yours.
Thank you very much. Thank you, everyone. And thank you, Vakshi. Also, thank you for NSRS in Nepal. It's really, really nice to be there. I wish I could be there in person. So maybe next time. So let me start by sharing my screen. I hope you can
Even
see
if we
that.
before we begin, Professor, I really
Yeah.
have one question I need to answer. You need to answer first.
Yeah. Yeah.
So like me- like what motivated you to do like physics, theoretical physics, like graviton, string theory? Like what is the reason behind your motivation? Like because I don't
Yeah.
want to be I don't want to sound like a discriminatory, but like I
Mhm.
myself don't see like there is many there are not much it will sound very bad, but there are not much like women pursuing theoretical physics. I don't want to sound bad, but like I think it is so. Like you are an exception in our field, an amazing exception. So what is like you? What motivates you to wake up every morning and like write equations on board?
Yeah, I think it's funny because I think we all have it in ourselves to be physicists and to want to understand the world and nature around us as well as possible. I think when you see kids, when you see everyone around us, they're really eager to understand. They're very curious, and then these develop in different ways for different people. For me, I was always eager to understand nature and the nature of reality at the most fundamental level because everything else was so complicated. And so that's what drove me to theoretical physics. That's what drove me, in fact, to gravity, to cosmology, and understanding gravity as a quantum field theory, because in fact, that's the only thing that remains once you take every other complications away. So it's almost the bare minimum, the simplest thing that you can imagine. If you take every other distraction away, the most fundamental elements in nature is space-time, and you need to understand it as a quantum phenomenon. So, in fact, to me, there was never any notion that there would be anything else because that's the most fundamental thing. And I think we all have it in ourselves to explore something as deep as possible. It's really exciting. And of course, the research every day has ups and downs. You try a lot of things and then it doesn't work out, and you feel like you spend years and years trying and it doesn't work out. But when it works, even when it doesn't work out, and when you understand something for yourself, is so satisfying, and you really have the impression that you're making progress, not just for yourself, but for humanity. We're pushing forward knowledge for humanity. And I think this is um, it's the most powerful thing there is. If we take everything away, what we have as human, which is completely universal, is a knowledge, and pushing that further is something we can all do. So I hope you're all going to be pushing it as well, much more than we do. As you know, we are stuck in many questions. So there's so many things to resolve still.
That's
There's so
one
many
of
open
the
questions.
that's a really good answer. Like for me, it was Greek alphabets, but that is a really good answer.
Okay, thank you. So, um, I hope you can see my screen here, and I'll try to be as interactive as possible, but we'll see how that goes. In fact, I love this picture. It's not a scientific picture, but I think it represents very much what the logic of what we're trying to do as an effective field theory, particularly for gravity, but in fact for all of the laws of nature. We're trying to connect the world where we stand at low energy. So we stand on the ground here, we can probe, we can make experiments, we can make observations at low energy. But ideally, we like from those to connect to an ultimate, to the new layers of physics, the new layers of reality. And so that may manifest itself as an underlying theory of everything, an underlying theory of quantum gravity. And that can be string theory, it can be some extension of string theory, it can be something else. And possibly we won't know just yet. Possibly we will never know precisely, but it doesn't mean that we can't make connections between the ultimate realization of reality and the low energy world in which we live in. So this is very much the framework in which I'll be talking about. So let me see if I can go here. I hope you can see those slides. Can you see that you went through? So I'm gonna describe things as a function of, sometimes I talk about energy, high energy or low energy. Of course, I don't really mean energy. I mean something which is more of a scalar quantity. Most of the time, I really have in mind curvature or something which is frame invariant that all observers can agree on. But we can think of the low energy world or the low curvature world and the high curvature world. And this is where we stand at the moment. We can make experiments for the in particle physics. We have made incredible gravitational observations for, we understand gravity in the solar system and in the galaxy, in the clusters of galaxies, and in the universe very well. We have detected gravitational waves. The community, us human, all of us, have observed black holes through black hole shadows, for instance, from the Event Horizon Telescope. And we are converging through a wealth of different data in a cosmological paradigm where all of the different kind of observations from supernovae to clusters of galaxies to the cosmic microwave background, even though they rely on very different scales, very different physics, very different instruments, very different assumptions, overall, they all seem to agree and converge in a very specific region of parameter space. So we're really doing a lot of progress in our understanding of the world as we think of it, what I'll consider being low energy. And for me, even the standard model of particle physics, even the Large Hadron Collider at CERN, even high energy physics in our everyday life, for me, this is low energy physics in the sense that we can use our quantum field descriptions to describe those phenomena. But ideally, we like to connect those observations and experiments with an ultimate theory of everything at high energy or at high curvature. And that can be foam gravity, it can be string theory, it can be something else, it can be other completion that you will come up with that I don't know about yet. But we'll like to be able to make connections between the two much better. And so, of course, this is the Holy Grail. This is something we would all like to do. And if it was so very easy, I wouldn't be there just to tell you about it. You will all know about it. So the approach that we can take is twofold. The first one that people have been considering is specialize in a particular high energy model. Let me say string theory is the particular realization of the world that you believe in. And then from that, you can try to cascade your way down to low energy theory and make some specific predictions at low energy. And 30 years ago, that's where we thought we would be, that we thought that we would have string theory with a particular realization, a particular brane embedding, a particular compactification, and from that we would uncover the standard model of particle physics and a specific realization of the world at low energy. But probably, as you know, this hasn't quite worked out like this. And in fact, even in string theory, there's a landscape of 10 to the 120 different kind of possibilities. So making the connection between the two is challenging. So rather than starting with high energy, a particular high energy completion, what I'll do is work my way up from the ground up. So I'll consider general relativity as the first term in a low energy description of the world. And then from that, we'll work our way up to understanding what kind of corrections there can be in general relativity. And those corrections, as an effective field theory, capture a lack of knowledge. And so understanding and parameterizing that lack of knowledge may enable us to determine in which direction we should be going towards our UV completion. So that's the effective field theory approach that I will be following. So I don't know exactly how much time we have, but we'll see. I'll talk, and when you're fed up with me, you can just make me stop, and and we'll go from there. So what else?
As long as you want.
Okay. So we'll see. So I know you all know Maxwell photon and Maxwell theory, and this is all known things for more than 100 years. But I think it is useful to start with this because it's a very simple model where a lot of the features that we can apply then for gravity can already be present, and we can explore them in a very simple way without being too scared about or too overwhelmed with some of the complications that come with gravity and the nonlinearities that come in. So I'll start with describing what I mean by a photon, and we'll uncover from that Maxwell theory of electromagnetism. And then we'll do the same thing for gravity. We'll start with what we consider the effective field theory for a spin-2 field, which will end up being the graviton, as we will see. And from that will emerge general relativity. And once we have general relativity, we can see how we can embed that into an effective field theory with implication for high energy completions. So this is more or less what I try to be doing today. Everything I'll be talking about today will be in 4 dimensions. It's very easy to generalize that to any number of dimensions that you want. So I just do 4 dimensions to be more concrete, apart from when we're doing dimensional regularizations. And then I'll be working with a Minkowski metric, having this form in units where C is h bar is 1, and the Planck scale is given by the Newton parameter like this. And throughout everything we'll do, I'll assume that we have fundamentally the theory of everything at high energy is fundamentally Lorentz invariant, in the sense that even though the world in which we live in, the realization that we experience today in the universe, in whichever room you are on Earth, clearly spontaneously breaks Lorentz invariance, it spontaneously breaks Poincare invariance. But if we were to zoom to very, very small distances in space-time, we expect to recover local inertial frame, we expect to recover Minkowski and a notion of Lorentz invariance. So that's why I'll start with Lorentz invariance. And then within a low energy effective description, I'll start with locality. I'll just build my theory as a local effective field theory. So you're only affected by your local neighborhood. And then the completion at high energy can, for instance, be string theory, which violates some level of locality because strings are extended objects. But that violation of locality is not relevant for the way we want to frame the low energy effective field theory. We can parameterize that very well if you're interested in, but I won't go into that too much right now. Okay, so as promised, we'll start just as a toy model for the photon, and we'll derive from that Maxwell theory for electromagnetism. So I'll try to write down a few things, and I hope this will work out. Thanks to Raksh, we tried that the other day, and it seemed to be working out. So let's see. So what I have in mind is because we are fundamentally having Poincare invariance, Lorentz invariance, we have a Minkowski metric. Let me start with just flat space-time, and I'll consider, because we have Lorentz invariance, we can describe the field as representation to the Poincare group, and I can describe a particular field with its mass and with its spin. And so one of the representation is a spin-1 field. In fact, I should have written in here that what I consider in here is a spin-1 field. So it transforms in a particular way under Poincaré invariance. And for now, I'll consider it to be massless. This doesn't matter too much, but I can do that for now. So by spin one, really, because we are in Minkowski, I have a notion of Minkowski metric. I can consider some Poincaré transformations, which is Lorentz transformation plus translation of this form, for instance. And a vector field will transform, the spin one field will transform as mu alpha A alpha of x. So this is what I mean by a spin one field for now. It's a vector field for now. And I'll assume locality as I mentioned Lorentz invariance. So with that in mind, if I want to have locality, what I mean by that is I want to write down operators which only depend on the field itself and on the derivative of the field and not on non-analytic behavior of the derivatives of the field themselves. So I can do a well-defined expansion about the vacuum. So the possible operators that I can write down for the kinetic term of my spin one field, I can write down something which looks, for instance, like d mu a nu and then d mu a nu. That's one operator I can write down. Then I have another choice, which is a2. I'll capture that with another coefficient, d mu a nu, d nu a mu. That's another kind of operator. Actually, let me start with, sorry. So I'm consistent with my notation. I'll write the alpha A alpha and then d beta A beta. So this is a scalar quantity. Here I have another scalar quantity. And then in principle, I can also write another operator, which is what I had written before, d mu A nu and then d nu A mu. However, you know that by integration by parts, this is equal to d nu A nu, d mu A mu, so it can be absorbed into the A2 term.
Hi, sorry, can I ask a very small question?
Yeah.
So these coefficients, are they going to be like complex or real, or it doesn't explicitly matter?
Excellent, excellent. Yes. Okay. So that's an absolutely excellent question. Thank you very much. So first of all, my Lorentz vector here and here, it's a real field. In principle, I can make it complex. That's absolutely fine. But just for simplicity, I'll start with it being real. And I want unitarity. So that's an amazing question. In fact, very relevant. I'm going to assume unitarity. So it's more easily expressible at the level of the Hamiltonian. I want the Hamiltonian to be Hermitian, but really what it means at the level of the Lagrangian is that I need it to be real. And so if the vector fields are real, the derivatives are real as well, the coefficients A1, A2, A3, they need to be real coefficients for now. So that's all I know so far, but they will need to be real. That's absolutely that's absolutely right. If I were considering a more sophisticated theory, I can start having some coefficients which are complex, but ultimately I like my Lagrangian to end up being real.
All right,
And
thank you.
Yeah, thank you. Yeah, thanks for the question. So in principle at this level, and this is in any number of dimensions, I focused to 4, but in fact that parametrization is in any number of dimensions if we want to. We have three free coefficients, real coefficient, A1, A2, A3, but you can see that the operator captured by the coefficient A3 after integration by parts can be absorbed into the A2 term. So for now, I'm simply gonna ignore these A3 terms. It's not independent. And so my real independent parameters are A1 and A2. So that's all we have so far. Okay, so in principle, I could have written down the kinetic term for any vector field in 4 dimensions like that. And if I write down with A1 and A2 real, a kinetic term like this, then in 4 dimensions, the vector field A mu has a priori 4 degrees of freedom because there's 4 components in the vector field A mu. But now, if we're dealing with a Lorentz invariant theory, we know that there's a difference in sign between what happens along the time direction and what happens along the space directions, which means that if we have a vector field that generally carries 4 independent degrees of freedom, by Lorentz invariance, we know that one of these degrees of freedom will always come in with a negative sign. So I'll show you that in different ways. But having a degree of freedom that comes in with a negative sign is a pathology which we cannot live with, and so we'll need to deal with that in a way or another. So I'll show you why this is the case in 2 different ways. I expect you probably know more or less what happens for a vector field, but this is useful for us to then being able to derive what happens for gravity, or for a spin to field, for the graviton, and then building our way to gravity. So for instance, we can see that the different degrees of freedom, if we have A1 and A2 as 2 independent free coefficients, real, we can take situations which are homogeneous. By that I mean that the spatial derivatives are 0. So if I look at here and I have that the spatial derivatives are 0, so I just have mu is time-like in here, alpha is time-like here, and beta is time-like here. What I have for the first term is minus A1, and then I'll have the time derivative here and the time derivative there with a minus sign for one of them. So it's plus A1, and then I'll have A0 dot squared, and then a minus A1 and a dot I squared. I think that's what I have. In fact, it's the other way around. I think it should be the other way around. Minus that and then plus this. And then for the A2 term, if I only have the time derivative, then that tells me that I have plus A2, and then I have an A dot 0 squared that comes in. So from that, I can see that in order to have this connected term, which is has the right way around for the sign, I need A1 to be positive. But at the same time, for this to be the right way around, I need A1 minus A2 to be positive as well. So this is the conditions I would need to have for the kinetic term of my spin 1 field to be positive in this homogeneous situation. Now I can imagine as well a static situation where the time derivatives instead are 0. If I take the time derivative instead to be 0, what I have is just the spatial derivatives in here, just the spatial derivatives in there. And so I end up having A1 dIAJ squared plus A2 dIAI squared. And then from the first term, I had as well minus A1 dIA0 squared. And so I can see from that in order for this term to have to be the right way around, I need the coefficient A1 to be negative. And so I already start saying that there's a contradiction between the 2 statements that I have in both situations. And so in principle, I can't have the kinetic term being, or the situation being stable both in the homogeneous situation and in the static situation, for instance, for the A0 term, unless there's a specific value of the coefficients that I have in these cases. So that's just a quick way to see it, but let me now go into a little bit more details of how we can see the problem arising. Sorry, my computer is lagging, so. Let me just say what I mean by the pathology that comes in when we're dealing with theories for which the kinetic term is potentially negative. So the situation in a quantum field theory, or even in a classical field theory, in fact, where one of the degrees of freedom has a negative kinetic term as compared to another degree of freedom, is called a ghost. So for instance, here, just for to show more precisely what the situation is, I consider 2 scalar fields. So these are 2 real scalar fields, it's just as an example. I have one scalar field which comes in with a standard kinetic term, when we have a mainly plus signature of the metric, and another kinetic term which comes with the opposite sign. And then I can add a potential. That doesn't matter too much. When I have 1 degree of freedom that comes in with the opposite sign as compared to the other one, then the kinetic term will have negative energy, and that corresponds to an unstable situation. And it's an unstable situation which is much worse than other kind of unstable situation that you may have heard of, for instance, a tachyon-like instability. So I'm just gonna mention that in here because sometimes you hear that we know there are instability in the real world. We know, for instance, that the Higgs potential at some point in the history of the universe probably had a tachyonic instability, and that's not necessarily a dramatic thing. We can live with that. When we're dealing with a tachyonic instability in the potential, so this is, for instance, let's imagine that's the Higgs scalar field or whatever scalar field you may imagine, and it has the wrong sign for its potential. So here the mass term squared is negative, if you were, so the potential has a region where it's curved the wrong way. So you can see that you have an instability in here. Typically, when that happens, that tells you that rather than looking at a situation where you should expand around the point in here, which is unstable, you should go around a different point in the potential. But also it tells you that the scale of this instability is governed by the slope of the potential. In this case, is governed by the scale m. And so you can tame that instability by making that scale m as small as you want, and then you have a very slow instability. And so if the mass is very small, then it is true that you will be driven away from the point phi 0, but you're going to be driven away from it quite slowly. And so it's not an abruptly fast instability. And this is different as compared to a ghost-like instability, where the scale of the instability is carried by the kinetic term of the field itself. And that's dramatic. I don't mean that in an existential point of view, but this is very different because if the scale of the instability is carried by the kinetic term, by the momentum of the field, if you were, then you have no way to switch it off. You can actually have the field going as fast as you want, and the faster the field goes, the quickest instability it is. So there's no way to tame it down in the same way as what would happen in a tachyon-like instability. So ghost degrees of freedom are degrees of freedom who have the wrong kinetic term, and that are instabilities which are arbitrarily fast, and we don't want to have such degrees of freedom in a theory, at least not at the linear level, because then we can't really define a vacuum for the theory, and we won't be able to quantize the theory later on, but we also don't have a starting point to describing the theory whatsoever. So in the case, yeah,
Excuse me
is that a question?
but I think as you were saying about like the ghost particles, yeah, not the ghost particles, the like ghost theories, like one they cause like instantaneous decay of everything.
That's right, exactly. So that at the classical level, that corresponds to an arbitrarily fast instability. What happens at the quantum level is that you can't prevent, as soon as you start having interactions between the two fields, phi and chi, you can't prevent but decaying the ghost field into the healthy field. So in some sense, producing the ghost field releases energy which can be used for the healthy particle to produce this the healthy particle. So as soon as you have interactions, and when we're dealing with gravity, everything interacts with everything else, having a ghost corresponds to an instantaneous decay of every particle into the ghost-like instability. And in fact, any particle can decay into the ghost, and that releases energy, and so that enables you to decay even more. So what it really means is that you have no ground state to start with, and there's actually no vacuum energy level with ground state that minimizes the energy. So you can't even start thinking about that theory. You can't even start thinking about quantizing it and using it to describing the world around us. It's a thick theory. It's not describing anything meaningful at all. So this is to say that we really don't want to start expressing quantum field theory for spin 1 and even less so for spin 2 if we already have degrees of freedom with ghosts with the wrong sign kinetic term. So when we're dealing with let me see. When we're dealing with when we're dealing with electromagnetism, when we're dealing with a vector field, which will later on being a photon or electromagnetism, if it were true that we had 4 independent degrees of freedom, we know that one of them, for instance, the A0, would always come in negatively for the kinetic term in the Lagrangian, and so we're always coming with the wrong sign in the Hamiltonian, and so that corresponds to a ghost-like instability. And one way to understand this is to think of what these degrees of freedom for the vector fields are. And so if I just talk about a vector field, it may seem a little bit abstract, but I can think of it as we know for electromagnetism, for instance, and then we know that in electromagnetism, in the vector degree of freedom, in the photon, there should be 2 polarizations, 2 degrees of freedom, which we typically describe as the 2 transverse polarizations, the E and the B field of electromagnetic waves, for instance. But in principle, in a vector field, we have 4 degrees of freedom, and in addition to the 2 transverse modes, so those 2 transverse modes are transverse to the line of propagation, there can also be a mode which corresponds to longitudinal fluctuations. And so it goes back and forth, because if you're considering potentially a vector field with no particular symmetry whatsoever, you can't prevent that vector field to not necessarily travel at the speed of light, and so you can have fluctuations along the line of propagation of the vector field. Those are longitudinal mode, and it is this mode which always comes in attached with a ghost-like instability. So to see that much more clearly, I think it is useful to separate out the different components in the vector field. I can write the vector field into a component which are the transverse components, which we know and like, and we know are present in electromagnetism. And those are transverse, which means that this is the condition for it to be transverse. These are the transverse mode. So they are orthogonal to the line of propagation. But in principle, if I'm not very careful, in addition to this transverse mode, built into the vector field, there's additional modes. And so let me just call this the longitudinal mode. And because it is a longitudinal mode, that corresponds to something which is along the line of propagation of the of the electromagnetic waves. So this is what we call here the longitudinal mode. So if you imagine, for instance, that you have an electromagnetic wave which is traveling along the z direction, this component here will pick up a component along the z direction. So this is the longitudinal mode for the vector field. So of course, you all know what the solution is, what the situation is in real Maxwell, in real electromagnetism. But if I'm not careful, and if I enable myself the possibility for my vector field to be expressed in terms of its kinetic term with any arbitrary coefficient A1 and A2, then in principle, I will excite not only the transverse mode, but also the longitudinal mode. And so if I go back to what I wrote before, we have in the kinetic term for the spin 1, we have a contribution which comes in from this A1 term, and another contribution that comes from the A2 term. And now I have split my vector field into the transverse mode and the longitudinal mode. This is the condition for it to be transverse. Now, if I focus on the longitudinal mode, just because this is where I know some of the instabilities will kick in, then just expressing the components that I have for this longitudinal mode, what I can see we having is, let me write. The first term is A1, and then it's d mu chi, d mu d nu chi. This is what this first term gives me if I just focus on the longitudinal mode for nu. And then the second terms give me plus a2 d mu chi, d nu chi. And so, in fact, those two terms are the same. May not be completely obvious, but they are the same. This I can write down as, this I can write down as box chi squared. And then this term here, by integration by parts, I can write it as also d mu chi, d nu chi by integration by parts. So also have box chi squared. So as a whole, what we have in here is a1 plus a2, and then box chi squared. That's what we have. So I don't know how obvious it is for you in here, but this is a term which is higher order in derivatives. Oops, sorry. And we can see that directly by looking at the equations of motion. So if I were to take the equations of motion for this term, for the chi term in here, what I will get is dl over d chi is box chi squared is equal to something. And that involves some chi to the 4 derivative plus other things. So this is a term which has higher derivative, more than 2 time derivatives. And so that means that the solutions, for instance, if you have an equation of motion which is box chi squared plus omega squared chi is equal to 0, then the solution are just e to the plus or minus I omega t. And so these are oscillating solutions. But if I have something which is 4 derivatives, and then let me write plus omega squared chi, I will also have not only some plus and minus I omega t, but I also have some one mode which grows exponentially. And so having terms which more derivatives involves an exponential growth already at the classical level, and that is the instability. And you can see that typically the scale of this growth instability is related to the 3 momentum, because in this equation there will also be some 3 momentum that will come in. And so that's one of the reasons, one of the ways to see why if you have a vector field and you allow for arbitrary coefficients for those operators, then typically what will happen is that the longitudinal mode becomes dynamical. And so not only you have an additional mode related to this longitudinal mode, but in fact, there's 2 degrees of freedom hidden in this longitudinal mode because it's a higher derivative operator. And this higher derivative operator always enables for an exponential growth, which is carried by the spatial momentum of the field and therefore can be an arbitrarily fast instability. So one way to see,
sorry. Can I ask possibly something I'm wondering? It might be a bit of a silly question, but I still want to ask it. Is there a way of possibly kind of reparameterizing T, like and that still preserves the gauge symmetry of the theory? I'm not sure.
Very, very good. So right now we have no gauge symmetry. At the moment, I haven't mentioned anything by gauge symmetry.
Oh, yes, true.
So that's excellent. You're absolutely right, and you're one step ahead of me, because that's exactly the solution. What we need is to impose a gauge symmetry so that this mode is actually not physical. It's just a gauge artifact, and has no physical relevance. So this is exactly the key point. You got your, what do you say, your dot on the money? Or yeah, you're exactly right. What you want to do is making sure that you parameterize your theory in such a way that you have, in fact, a gauge theory. So yeah, let me go through that. Let me say a few things, and if I haven't completely answered your question, ask again. Yeah. Okay, but you're absolutely right. This is the key to the question. But let me first say, in this the Ostrogatsky theorem tells us that a term which has higher derivatives, like this term in here, has in fact 2 degrees of freedom hidden in it. And so one of the ways to see it is to look at the propagator for a field which involves higher derivatives. So the propagator in here is box squared, rather than being 1 over box, is 1 over box squared. And that I can always think of it as the limit when m goes to 0 of the difference between 2 ordinary propagators. So this would be an ordinary propagator with a tachyon, and then another ordinary propagator with a negative sign. So let me really put that, because this is the important part in here. This comes in with a minus sign. So you can see that if you take the difference in here of those, oops, sorry, let me make that a bit smaller. If I take the difference between those two things, I get in here box plus m squared minus box plus m squared over box squared minus m to the 4. And so if I take the limit where m goes to 0, this will disappear, and this will give me 2m squared over box. And so if I put a 1 over 2m squared here, in the limit where little m goes to 0, from this difference between those two propagators, I indeed get that propagator here. That's a higher derivative propagator. So any higher derivative propagator, any degrees of freedom which involves higher derivative in the Lagrangian or in its equation of motion, from that you can see that the propagator can actually be written as the difference of 2 otherwise more ordinary not high derivative propagators, one of them coming in with a tachyon instability, but that is okay because we're going to take the limit where the mass goes to 0. So that's not really the problem. But the problem is that one of them always comes in with a wrong sign. And so hidden in chi, there's actually 2 modes, one mode which is healthy and another mode which has always the wrong sign kinetic term, the wrong sign propagator. You can rewrite this, in other words, as well, into saying that in the equation of motion, box chi is equal to 0. I can rephrase this into writing, for instance, box chi is equal to chi tilde, and then box chi tilde is equal to 0. So I introduce another field chi tilde, and so that means that in the Lagrangian for box chi squared, if I write this as box chi squared, I could also have written it in terms of what seems to be more of a Lagrange multiply chi tilde as something like this. So you see that if I have a Lagrangian of this form, where I introduce, I not only have the chi, but I introduce an auxiliary field chi tilde, we can see that the equation of motion for chi is simply box chi tilde is equal to 0, which is the equation we had in here. And the equation of motion for chi tilde is box chi is equal to chi tilde, which is the equation we got in here. So this higher derivative Lagrangian can be written as the Lagrangian for with just 2 derivatives for the scalar field chi and then an auxiliary field chi tilde. But now if I make a decomposition of chi is equal to phi1 plus phi2, and chi tilde is the difference between those two fields, minus phi2, then what we can see is that this Lagrangian for box chi squared, I was written in it before, is phi1 box phi1 minus phi2 box phi2. So chi tilde box chi is phi1 plus phi2 box phi1 minus phi2. So it's this thing here. And then we have, this is a mass term for those two fields. That's okay. I can write this as minus a half phi1 minus phi2 squared. So this mass term here, or this potential term, is not really important, but really the crux of the matter is as this part of the Lagrangian looks like the kinetic term for a scalar field phi2, which has the wrong sign kinetic term. So this is always the wrong sign. And so once again, in this higher derivative operator, I can always express it in terms of two fields, one which has the right side kinetic term and one that has the wrong side kinetic term. So this one is a ghost. So as soon as my Lagrangian involves higher derivatives, we know that there's a ghost degree of freedom in there. So this is exactly the situation we had before, where we had two scalar fields with opposite sign kinetic terms, and then they couple together. We know that this always leads to an instability, arbitrary fast instability, unless there's a way to ensure that these higher derivatives are not present in my theory. And so the only way for us to ensure that these terms are not present in a theory is to not set A1 and A2 be completely arbitrary, but in fact have A1 is minus A2. So unless this chi mode disappear entirely, unless chi disappears entirely from our Lagrangian, so unless we have A1 is equal to minus A2, we have an instability. And so that means that for chi to disappear entirely from our theory, we need to have a symmetry. It means that the Lagrangian should be symmetric under A mu. Oops, sorry. A mu goes to A mu plus d mu chi. Because this is precisely what we did to start with. We started by splitting the vector field into a mode here and then a longitudinal mode. And we saw that as soon as the longitudinal mode appears, then we have higher derivatives, which lead to ghost instabilities, arbitrary fast decay of the modes into one another, which we cannot live with. So the only way for the theory at hand of a vector field to be meaningful is if we have a symmetry. And in this case, as you were exactly saying, this corresponds to the gauge symmetry. A mu goes to A mu plus d mu chi. And the theory should be such that chi does not appear in the Lagrangian when we make that split. And therefore, that corresponds to the U1 gauge symmetry. So I'm emphasizing this because typically, at least when I learned it in college or when we express it, we typically start by the assumption that you have a gauge symmetry, and then we ask ourselves the question, how can we write down the kinetic term for Maxwell in such a way that the gauge symmetry, the U1 gauge symmetry, is preserved? But in fact, if we want it to be pedantic, it's the other way around. We can start with anything you want, but you need to have a gauge symmetry for the kinetic term to be stable. And so it's not like the pillars of electromagnetism should necessarily be gauge invariants. The pillars of electromagnetism are stability, locality, unitarity, and Lorentz invariance. And based on that, we see that we need to have gauge invariance to ensure stability. And so this is important because it will be the same thing for general relativity. So the bottom line for a vector field, and we recover from the vector field, the stability of it requires gauge invariance. So we only started with a Lorentz vector here in 4D, but all of these arguments work in higher dimensions as well. And we see that we assume unitarity, but that doesn't play such an important role in here, other than through stability. So assuming locality and Lorentz invariance, we saw that the Lagrangian could be written like this, but the kinetic term for the spin 1 field is unstable unless there is an additional symmetry, which sets up that really what it means is that A1 has to be equal to minus A2. And so that way the kinetic term is stable. So the U1 gauge symmetry in this case is there to ensure the stability. So it's somehow a consequence as opposed to an assumption of the theory. So with this U1 gauge symmetry, you can start now with the spin 1, or with really the assumption that A1 is equal to minus A2. And just for definiteness, I can always scale things away. Now let me set A1 is equal to a half. You can take it any value you want, really, but let me set it to be a half. So just for normalization. So in this case, we have d mu a nu minus d mu a nu minus d mu a mu d nu a nu. So this is the kinetic term we started with. Now with the assumption that A1 is equal to minus A2. This is what we were built towards. So that corresponds to a half d mu a nu, and then d mu a nu, and then from here I can do some integration by parts in there, and that gives me minus d nu a mu. And you can see now coming in is the Maxwell tensor, the Faraday tensor for electromagnetism, and really that corresponds to 1/4 F mu nu, F mu nu. And really, sorry, I should have done it the minus here. So that's good. I did it the wrong way around. That should be negative if I want my theory to have the right way around. So we recover from the Maxwell theory of electromagnetism with the only assumption of stability, locality, and Lorentz invariance. And gauge invariance comes in as a consequence of that. So that's what I wanted to say, just as a toy model to start with for electromagnetism. Is there any question about this? Did I answer your question, Nazir? Yeah?
Yes,
okay.
it's all good.
Okay, excellent. So thanks for this. So now, really, what we're more interested in, I think, is not well. Electromagnetism is great, light is great, the photon is great. And let me just say from here, now that we have here, we have this starting point, we know that we have a gauge symmetry. We know that the theory is stable like this. We can quantize the vector field, a mu. And in this case, you know that you have a gauge symmetry, so you need to be careful when you start quantizing this field, but you know how to do it. And upon quantizing it, then you know that this vector field will end up being the photon. Okay, so now let's just do exactly the same thing for gravity. So let's start with now in this case a spin-to field. We'll look at what happens at the linearized level. We'll build our way up to general relativity when you have interactions. And then we'll look at an effective field theory. We'll look at the connection between the UV and the IR, the cosmological constant problem, and the effective field theory, and connection with the high energy completion. So that's what I'll do in the next hour or so, probably. So let me start with this beautiful paper from Weinberg, which really shows how the standard model of particle physics and general relativity should be considered as the leading terms in an effective field theory. So this term here is just the least suppressed term in the Lagrangian. In fact, it's really the cosmological constant, but when he wrote that, this one here probably wanted to set the cosmological constant to 0. And so this is the approach that we will be taking. Now to do the same thing for gravity, and we'll think of the effective field theory of gravity, what we can start with is just doing the same thing for a spin-to field. So in exactly the same way as we thought of Maxwell theory for electromagnetism as the unique theory for a gauge vector field and spin-1 vector field. Now we're going to extract ourselves from everything you ever knew about general relativity and gravity and the graviton. Just forget everything, and let's just imagine that we following the same route of characterizing the different representations of the Poincaré group. So you can do it for a spin 0, which is a scalar field. You can do it for a spin 1, which is a vector field. You can do it for half integer spins as well. We're not going to go through that, but in principle, you can go through all of this. And then the next one on the list, naturally, is the spin 2. So let me write the spin 2 h mu nu in Minkowski. So I'm still assuming that we have fundamentally Poincaré invariance. I can do those representation. And so if I have Poincaré invariance, I can write down for Poincaré, I have x mu goes to x tilde mu, is equal to lambda mu alpha x alpha plus, so this is the Lorentz invariance, and then let me say 0. This is the translation invariance like this. So this is my Poincaré transformation. The Minkowski metric we know is invariant under Poincaré transformation. We knew how the vector field transformed. We've done that before, so let me not write it in here. And now the next one on the list is a spin to field. Let me say a tensor field if you want to. And this I wanted to transform as x tilde, which is lambda mu alpha, lambda mu beta, h alpha beta of x. So this is roughly, in fact, my definition of my tensor field so far. I wanted to transform like that. It's a particular object that transforms in a particular way under Poincaré invariance, and that makes sense to represent things in this way because we are thinking that we have ultimately, fundamentally, Poincaré invariance as a theory of everything. So this is my fundamental object I want to start working with. And so I will do the same thing as we did for the spin one field. I can start by writing down the kinetic term for my spin two field. And just like what we did for the vector field, the kinetic term is something which is local, Lorentz invariant. So I want to construct scalar quantities. So I need to contract all of the indices. And I want it to be of this form with no square root of derivatives or anything which would be non-local. And again, I'm going to assume unitarity in the same way as we did before. So this tensor field is a real tensor field for now and forever. We could, in principle, think of having complex ones. And in fact, I've been working in charged massive spin two fields. It's a very interesting story in itself, but we're not going to do that today. So for now, this is just going to be real. And so all the coefficients that we're going to write down in here are also going to be real. And so what we can write as the different terms in there, in this case, it's the same. It's just because it has more indices, you have more possibilities. So let me just go through all the different contractions that we have. So if I start with d alpha h mu nu, so this would be the first term in here. The other term in here, what we can write down, let me write a b1 d alpha h mu nu. That's one way I can contract it. Or another way to contract it is b2 d mu h alpha nu. And because I want it to be symmetric under mu and nu, I'm going to make it symmetric under mu and nu in here. So I'm going to make it symmetric there. Those parentheses just mean it's symmetric under that. Another way to do it is to write B3 and then H beta eta mu nu with a D alpha in front in here. That's another way I can do it. And then finally, another way we can do it is to write B4 and then D mu, the trace again, H eta nu alpha. And because it's symmetric under mu nu in here, I want it to be symmetric under mu and nu in here. So I'll put some parentheses in here. I'll put a factor of 2 in there. And I close that here. And in fact, I think with my conventions, there's a factor of 2 in here, I believe. So I have that. So, okay, so these are all the, no, it's a bit squeezed in here. So let me just rewrite this slightly. So it's plus 2 beta 4 and then d mu h eta nu alpha. Okay. So these are the different type of contractions that we can write down. You may think of other ones, but believe me when I say that anything else that you may want to think about after integration by parts can be rewritten in this form. So I think that's all we can have in here. So the derivatives can be either carried by alpha or by mu and nu, and then you can either have the tensor itself or you can have the trace, in which case you need an eta mu nu, and that's what there is. Now, in this exactly the same way as what we did for the vector field, in principle, our fundamental object h mu nu is a tensor. And so how many degrees of freedom do you think there is in h mu nu a priori, if I don't do anything extravagant. Does anyone know?
8 maybe?
10.
I got 8, I got 10. These are all good answers. Yeah. Anything else?
If we assume
It would be
symmetry,
4 by 4, so 16, but then it's due to asymmetry, we would have, I think, 10.
Yeah, okay, so it's 10. And then you're absolutely right. Yes, so you're absolutely right. I haven't said in here, I'm going to assume that this object H mu nu is symmetric under nu mu. I can build another object from that, which is antisymmetric, which is sort of corresponding to torsion. And that torsion, I can always express it in terms of lower spin additional degrees of freedom. So you're absolutely right. I should have said that. So indeed, a priori, this I can write it down as a symmetric 4 by 4 matrix. So if it wasn't symmetric, it would have 16 components, but because it's symmetric, it has 10 degrees of freedom. So H mu nu can, in principle, have 10 up to 10 degrees of freedom, which is a lot, right? How many do you think we really want to have in H mu nu?
2?
Yes, exactly. You really, really want to have 2, just like in 4 dimension, just like for electromagnetism. So that's really, really far too many. It's 8 too many degrees of freedom, 8 too many degrees of freedom. So we're gonna need to do something about that. So DOF are degrees of freedom. And so just in the same way for electromagnetism, we started with a priori having it 4. And once we imposed the gauge symmetry, or the gauge symmetry was imposed on us by stability, that gauge symmetry, in fact, removes 2 degrees of freedom. And so we're left with 2 degrees of freedom in electromagnetism. Now, the same idea will be true for the spin to field. In principle, we start with 10 degrees of freedom. And we only want really 2 of them. So we need to remove 8 of them. And to remove 8 of them, we can impose 4 what looks like gauge symmetries at the linear level, 4 gauge symmetries. And each single one of those 4 gauge symmetries will remove 2 degrees of freedom. So there'll be 8 would-be degrees of freedom, which has just gauge modes now. And so we're left with 10 minus 8, which are the 2 corresponding degrees of freedom. So I'll go in a second into explaining how we can think of that more concretely, but really what we're gonna need to do is impose 4 local symmetries.
A question. So
Yeah.
this does not have the gauge symmetry as electromagnetism, right? So we have diffeomorphism invariance instead of gauge invariance. Am I right?
That's right, exactly. That's exactly right. So, and we'll see, this is gonna come to us. You don't even need to know about it. It will fall on us, literally through gravity. It will fall on us, exactly. So the symmetries are not exactly the same, but they are very similar at the linear level. And then we'll see how this diff invariance, linear diff invariance, can then be built into nonlinear diff invariance, which end up being full coordinate transformation invariance, exactly. So something you probably know, that's exactly right, yeah. Something you probably know in general relativity, you told me that you would expect there to only be 2 degrees of freedom, not 10. And I think we know this because gravitational waves have been observed. And we know that gravitational waves come with 2 polarizations. You may think of this as the plus polarization, and then this mode here as the cross polarization. So that the 2 polarization. In fact, it's not really the case that those 2 have been observed. What we observe is just a combination of both, but it's very consistent with gravitational waves carrying those 2 polarizations. So this is as seen from a straight-on view. If the gravitational wave is propagating along this direction, then you can see that it's a purely transverse degree of freedom. It doesn't move along the longitudinal direction. It's simply a transverse mode. So that means that in addition to those 2 polarization, 2 degrees of freedom, what can happen in principle if we were to think about an arbitrary spin-2 field, in principle, there could be 4 other modes. And just like we had in electromagnetism, we had the longitudinal mode chi. In that mode hidden, there were actually 2 degrees of freedom, the longitudinal mode plus the high derivative term, which is a ghost mode riding on top of it, like the phi1 and the phi2 being carried, both of them by chi. The same thing happens for each one of those. Now there are 4 longitudinal modes potentially that could be carried by the spin-2. Of course, we don't want them, but in principle, they could be present. So you have those modes here, which would correspond to more like vector modes. You see that they transform along they change things along the longitudinal direction and along the transverse direction as well. So in here, the straight-on view, you see that is not quite the same thing as the standard polarization, the plus and cross, because in that direction here, you see that doesn't change. It doesn't change in here, but rather it changes along the longitudinal direction. So it mixes the transverse and the longitudinal direction for 2 of those, and each one carry a ghost as well. So there's 4 modes really in here. And there's 2 also additional modes which look like scalar degrees of freedom. So this is a conformal mode, or what we think as the breathing mode, which is goes along the longitudinal direction, not so much, but along the transverse direction. And then this one is really the most problematic one. It's purely along the longitudinal direction. And if you look at it straight on face, it doesn't seem like it changes anything, but it goes in there. So each one of those also carry, in principle, a ghost with them. So there's, in principle, 4 degrees of freedom in here and 4 degrees of freedom in there. So we need to find a way, and I'm sure you can think of it, to remove all of those 8 degrees of freedom being there. And so for that, we'll see that will impose a similar symmetry as what we had before, but it will correspond to diff invariance in this case. So we started with a linear spin-2 kinetic term, which could carry all of these different kind of operators in principle, with the BI, B1, B2, B3, B4 being real. In principle, if we were to write it completely like that, we would have 10 degrees of freedom, but we know that's far too many. And so to see how to remove the additional degrees of freedom, the best is to do the same thing as what we did before for electromagnetism. I'm going to split my tensor mode into the transverse modes plus now the longitudinal modes. But because of the index structure, we have much more degrees of freedom in the longitudinal modes. So the H mu T in here, these are the transverse modes. So in the same way as what we had before, ensuring that transverse mode tells us that we're going to write it as mu nu is equal to 0. So that's the transverse mode. And then chi mu correspond to 4 longitudinal mode, which is what represented in the previous slide. So if I go here, those chi mu in here, they correspond to all of those 4 of them in there. But they carry ghost, and so that's why there's actually 4 times 2 modes in each one of them. So yeah, so that's what let me just write that here. In here. Okay, if I go in here, we have the transverse mode, we have the longitudinal mode, and I didn't want to go through all the details now, but you can, if you plug this split into the kinetic term for the spin-2 field, you can start with the terms which are just quadratic into the longitudinal mode, and you get these 2 different kind of combinations. So you have one which is a box squared, and then you have another one which is a box d mu d alpha. It's simply 2 different contractions of it, but they are high derivatives, as you can see. So the propagator will be box squared, and then it will be more complicated tensor structure, but it will still be a high derivative operator. And then similarly, when I look at the cross terms between the longitudinal mode and the transverse mode, you see that you have cross terms which are also high derivatives. So for instance, these 3 derivatives, these are 3 derivatives, etc. So in order to ensure that there's no higher derivative terms whatsoever in this Lagrangian, what you need to do is make sure that all of those terms cancel out. So you need this to be 0, you need this combination of coefficient to be 0, and then the blue combination of coefficient in here to be 0. So the only way to avoid high derivatives in this theory, and therefore to avoid ghost, is to ensure that the coefficient take a particular form. And the only choice that we have is to set B1 is equal to minus B2 from the first term in here. And then from the second term in here, you see that this should be equal to plus B4, because B4 plus B2 should be 0. And then B3 should be equal to minus B4. So this is minus B3. And so what we see in here is that the only way to ensure that there's no higher derivatives is to set off those coefficients. And when we set off those coefficients, this disappear, that term disappear, oops. This term disappears, this term disappears, this term disappears, oh, sorry, this term disappears, this term disappears, and then this term should disappear as well. So if I have B1 plus 3B2, that's minus 2B1, and then 2B3 plus 4B2, B4, that's 2B1, so this term disappears as well. And so when we set that up, then the longitudinal mode chi mu completely disappears from the expression in the Lagrangian, which means that it's a gauge mode. And so once again, ensuring that we have stability of the kinetic term for a spin-2 field tells us that we need to have this gauge symmetry. The longitudinal mode, as written like this, should be a gauge mode. And what you probably can see appearing in here is that if after a split of this form, the Lagrangian doesn't depend on this longitudinal mode, that corresponds to diff invariance. So this is a diff, this is a linearized diff. And if Lagrangian is invariant under linear diff, then you have linear diff invariance as a symmetry. And that choice of coefficients directly imposes what we call the Lipschitz-Moritz operator. So this thing in here tells us, if you go through it, we recover the Lipschitz-Moritz operator. Which is just another word for the linearized Einstein-Hilbert term. So what we end up in here is linearized GR. Even though we haven't postulated anything about GR, any of the pillars of general relativity or anything like that, it's not like we started by imposing coordinate transformation invariance or any of the or the equivalence principle or anything like that. Just from asking for stability of the theory, we are led to all of those symmetries being imposed on us. So if we this is what I just wrote before, and if I write down this choice of coefficient, what I end up having for my linearized kinetic term, setting now B1 is equal to a half, is h mu nu, and then this is the Lipschitz-Moritz operator, alpha beta mu nu h alpha beta. This thing here is just a derivative operator, second order derivative operator, which is the linearized Einstein-Hilbert term. So that's box h mu nu minus 2 d mu h nu alpha plus d mu d nu h minus eta mu nu box h minus d alpha d beta h alpha beta. And this happens to be the linearized Einstein-Hilbert term. If I write the metric as being eta mu nu plus h mu nu, which you can do if you want to. And that, by definition, is invariant and linear depth, which is h mu nu goes to h mu nu plus d mu psi nu. Because we chose the coefficient in such a way that if we did do that, the psi nu, or what we had as chi before, would disappear. So linear depth it actually comes to us, appears as the only way to ensure the stabilities. So the absence of ghost. So that's a symmetry which is imposed upon us without any guiding principle from the outset. Okay, any questions about this? If not, so now this is the just the linearized kinetic term, but of course that's not quite very interesting in itself. What we want to do really is to start understanding how we can probe this spin to field. So ideally, we want to couple this spin to field to some external fields, and the first thing we can do is to couple it to an external source T mu nu. And so I'm sure you know how to do that. This is just corresponding to something that looks very similar, very reminiscent to linearized GR, but in fact, I don't assume GR in any way in here. So we know that the linearized kinetic term is written like this, where this is the Lipson-Oritz operator that I wrote before. So this is just that operator in here. And then if I want to couple it to an external source, just like if I wanted to couple a vector field A mu to an external source J nu, I would add a term in the Lagrangian, which is A mu J nu. Now, doing the same thing for the spin to field, it just corresponds to coupling the H mu nu to T mu nu in this form. And so far, don't worry too much about the naming here. This is just the scale of that coupling. It's just to ensure that if this has dimension 4, T mu nu has dimension 4, and H has dimension 1, then I need something to carry the scale. And that's just what I call it. I could have called it lambda. It doesn't matter too much. But of course, it's not innocent that I call it the way I wanted to call it there. So the equations of motion in this case, simply if I vary with respect to H mu nu, and I want to 0, that will impose the linearized Einstein-Hilbert equation, but I don't need to know about those. And it tells me that the linearized Einstein-Hilbert term, this is G mu nu, is equal to 1 over m Planck T mu nu. And then we can see that the linearized F invariance tells us that the stress energy has to be conserved, demands conservation of T mu nu. So d mu T mu nu is equal to 0. And you can see that at this level in here, you know that if I take the transverse contribution to that, I'll get 0, which tells me that the transverse contribution to that with a partial derivative gives me 0. Or you can see it in here. If I make the substitution, H mu nu goes to H mu nu plus d mu psi nu, this is invariant under it. So this is invariant under H mu nu goes to H mu nu plus d mu psi nu. You know that because that's the way we derived it. So if I make that transformation for this term in here, what I'll end up having there is d mu psi nu t mu nu, twice symmetrized, but if t mu nu is symmetric, I can just keep it like that, which I can write as minus psi nu d mu t mu nu, and so if I want this part of the Lagrangian to also remain gauge invariant with the same symmetry, then it better be the case that my stress energy tensor is conserved. So at this level, conservation of an external source, and so far this is just an external source, doesn't carry any dynamical degrees of freedom, but the conservation of the stress energy tensor at the linear level is imposed upon us by the symmetry. And so I think this is probably reminiscent to what you may have seen in general relativity. So this is for an external source in the sense that I haven't really thought too much about the degrees of freedom that makes that stress energy tensor. But in principle, we can think of having interaction between the field h mu nu, the spin to field, and other dynamical degrees of freedom. That's really what nature would be like. It's only in some very specific limit that I can consider the stress energy tensor to be fixed and to be external, but typically it will be carried fundamentally by degrees of freedom. And so the first thing we can think of, to be simple, is just to imagine that I have my tensor mode, my spin to field h mu nu at the linear level. Its kinetic term is given by the Lipton-Oritz operator, and then it couples to another degree of freedom that we consider a scalar degree of freedom, and that coupling is captured by the stress energy tensor of a scalar degree of freedom. So if I consider a scalar degree of freedom in Minkowski, we're just living in Minkowski so far, I haven't talked about gravity or anything like this so far. The stress energy tensor for that degree of freedom is simply given by something you've probably seen. So this is coming in as the quantity that is being extracted by Poincare invariance from this Lagrangian. So this is the stress energy tensor for a scalar field, and we can see that the conservation of energy momentum tensor for t mu nu impose the Klein-Gordon equation of the scalar field. So the conservation of t mu nu imposes the Klein-Gordon equation for phi. We can see that, for instance, d mu t mu nu is equal to 0. That tells me that from this term in here there's a term which is box phi, d nu phi, and then another term which is d mu d mu d nu phi. So that's from the first term, and this is from the first term in here, and then this will just capture the d nu. So I'll have from here, the 2 will cancel that one. We'll have minus d mu d nu phi d nu phi. So those two things cancel, and then minus v prime d nu phi. And so if this is 0, we get that box phi minus v prime d nu phi is equal to 0, and that has to be true always, which gives me the Klein-Gordon equation, box phi is equal to v prime of phi. So we see that a conservation of the stress energy tensor, in this case at the linear level, this is the partial conservation of the stress energy tensor, imposes the Klein-Gordon equation, which is indeed the equation of motion for my scalar field. This is the same equation as what I would have got had I derived my Lagrangian, my whole Hamiltonian with respect to phi is equal to 0. This phi Lagrangian here being 0 tells me that box phi minus v prime of phi is equal to 0. So far everything seems to be consistent, and so a priori, I could think that the naive theory for a spin-2 field interacting with a scalar, so I have, this is the theory, the kinetic term for a spin-2 field, this is my theory for a scalar, and then I want them to interact with one another, can be written like this, where now I'm going to say that this this is a stress energy tensor for the field phi, which is given by this. No, it does that. So a priori, this seems consistent, and I could start writing this down. However, are you happy with this? Let me just ask you. Are you happy with that?
Yeah.
Yes.
Yeah.
Yeah. So why isn't this the theory for general relativity? I have a linearized spin to field. I have a scalar field. So this, in principle, I can say this is general relativity coupled to a spin zero field, and I have this coupling there.
Oh, is it maybe because of the determinant of the metric that you need to worry about, or no?
So I haven't even talked about a metric.
Oh, yeah, sure. Yeah.
No, you're right. You're absolutely right. I should, but I haven't. But why? So why should I? And why am I driven to that? A priori, I can write this down. I want to have linear depth. Why is the fundamental theory of the spin 2 not just coupled to a scalar field, not just linear depth? In principle, I could just do that.
Is it because you need to, instead of looking at local conservation of the stress energy, but you need to look at the global conservation of it, like the
you're absolutely on the right track. Yeah, I need to be a bit careful. And indeed, it's related to this local local conservation of the stress energy tensor. So far, I looked at a sector which is just a spin 2 by itself, and I have different variance, and that ensures the stability of that sector. And then I have looked at just the scalar sector by itself, and I asked for the equation of motion for that's decoupled scalar degree of freedom. The equation of motion for that decoupled scalar degree of freedom tells me that the stress energy tensor is conserved. So those two things separately considered are absolutely fine. The issue is when I put them both back into the same framework. In fact, now, if I'm really honest with myself, and I ask myself the question, what is the truly, honestly equation of motion for phi? Is not just this, because in deriving the equation of motion for phi, I can't just focus on this term here. I can't just focus on this green term here. Phi comes in here. There's a phi contribution in here, which is given by that. And so when I derive the equation of motion for phi and I put everything back together, what I end up with are additional contribution. So in this case, the equation of motion for phi has ds over d phi total is what I had before, box phi minus v prime of phi. This is from the green term. I don't know if you can see the colors. So from that term in here. But I also have additional contribution from here, which have been more complicated. They are suppressed by that scale that are not so naively introduced as being one of implied, but it has contribution which goes like d mu h mu nu d nu phi minus a half d alpha h d alpha phi plus a half h b prime. And this typically is non-zero. This
So
is
you
of
have
the
to worry
order.
about the interaction term then also of
That's
the
right.
field.
That's
Okay.
exactly right. We need to worry about the interaction terms. So as soon as you have interactions, as soon as you want your spin 2 field to start interacting with something which is not just an external frozen degree of freedom, but a generally dynamical degree of freedom in its own right, for which I'm going to vary the action with respect to, I need to start worrying about the interactions. I want interactions, so then I'm gifted with them. I can't have my cake and eat it. Either I want interactions. If I haven't want interactions, then I actually need to understand how these interactions back react on myself, back react on things. And so the way that back reacts is telling me that the stress energy tensor is no longer partially conserved. This is no longer the case. This would be the case in here. This would be 0 if those terms there were not present. But actually, because of the interactions that I was asking for, I have additional contribution to the Klein-Gordon equation, which disturb my conservation of stress energy momentum tensor. Instead, what we have is d mu t mu nu is something which is of the order of h over m Planck. So my interactions start backfiring on me, and so we no longer have this the linear gauge invariance. So the symmetry is no longer conserved. And that's a problem. It's a problem for the symmetry no longer to be conserved, because if the symmetry is no longer conserved, I'm going to start exciting these additional degrees of freedom, all the longitudinal modes that we nicely switched off before. If they start being dynamical, then the theory is no longer going to be consistent by itself. So what we need to do is find a way to improve those interactions in such a way that we can have something like that at the linear level, but we need to promote the gauge invariance to something else in such a way that we recover some additional symmetry, even though we have a modification of the Klein-Gordon equation with powers of h over m Planck, and therefore a modification of the conservation law. You see that if this is not the case, if this is non-zero, then in here, when I set h mu nu goes to h mu nu plus d mu d nu psi, this will no longer be invariant. And so that's really an issue. So what we need to do, and then this is something which is imposed upon us, we have no choice about that, because we have a failure conservation of the stress energy tensor at order this scale. Of course, I call it m Planck for a reason, but we have this. It tells us that linear stiff invariance is also broken at that order. And so in order to make the whole framework consistent, we can no longer stop there. What we need to do is to supplement this linearized theory with some nonlinear corrections in 1 over m Planck. So rather than considering just this symmetry here, what we need to say is that we need to promote that theory to something which is less trivial, that will include some terms that go like h of m Planck, d xi, this is symbolically, right, plus h squared of m Planck, d xi, etc., symbolically. And there's all sorts of different index contraction that may come in here. And so the resolution is to promote the linear diff into something which is fully nonlinear in such a way that we have a nonlinear symmetry, and the stress energy tensor ends up having some other kind of relationship that enables us to remove the additional degrees of freedom, the longitudinal modes that we don't want to. So if I write this like that, what we really need is, in addition to this linear diff, we have a sum of an infinite number of nonlinear terms, which are all carried by some nonlinear powers of h over m Planck. So we have an operator here that involves some derivatives, and alpha mu nu, h to the n, and this is symbolic, and xi alpha, this is all symbolic, of course. So we can have all sorts of different interactions. And so what it also means is that we need to promote the interactions, not just to h mu nu over m Planck t mu nu. That's what we had before. So what we had before was that, which we call d mu phi, d nux phi, minus a half, eta mu nu, etc. This is just the linear term of the stress energy tensor for phi. That's just one thing, but we need to supplement it to an infinite number of other operators. So something that would go like Planck squared, d phi, and then something that will go like h cubed and h to the n over m Planck to the n, d phi, to all orders. And so as soon as you start switching in one interaction, one first order interaction between h and t mu nu, and you make the degrees of freedom in t mu nu being dynamical, then you can't stop generating a whole infinite series where you need to promote the symmetry to something which carries an infinite number of terms, a higher and higher order in H, and that generates the need for the interactions to also be populated to all orders in H. So you can never have just a linear interaction between H mu nu and phi. Of course, in some limit, this is the only thing that may be relevant. That's a different question. But honestly, fundamentally, this can never be the whole story. As soon as you have the first term, you're obliged to have an infinite tower of higher operators, higher order interactions between H and whatever dynamical field that you want. And if that happens as well, because the symmetry is now non-linearly realized, the same thing will happen for the kinetic term. So you don't just have H, the Lipson-Hurwitz operator that we wrote before, which is the linear Hansen-Hilbert term. You also have something which is nonlinear, so you have H squared, D squared H, plus an infinite number of operator. And this, in fact, corresponds to the energy being carried by gravitational waves. By the gravitational fields, if you want.
So when you do this expansion, it is still true that it is an asymptotic series, right? That because H is really small, it's going to converge.
Yeah, I
Okay.
haven't assumed H to be small in here. H can be small,
okay.
and if H
No,
is small,
true.
then you have a particular assumption, a particular meaning of the convergence of the series. But at no point have I assumed. I haven't.
The habit of assuming weak field limit immediately
That's
as
right,
I
that's
see
right.
the H,
So
but yeah.
That's right. That's what we like. When we talk about H, we typically think that what we have in mind is being small gravitational waves perturbations on top of flat spacetime, which may be the case. And if that's the case, then it's sufficient just to focus on this term. But if I think of cosmology, for instance, H mu nu is the departure of the metric as compared to Minkowski, and is something which is significant. And so each one of those terms, the whole thing converges, but each one of those terms is not necessarily small. So I make no assumption on the magnitude of those things. And if you're in curved space-time, in fact, this whole series resums to something very different as compared to what you had started with, and is significant. So the bottom line is that it's something we all know, and in fact, general relativity was first derived like this, so that's why it's easier to know what the answer is now. But if we didn't know to start with, if we were all just quantum field theorists to start with, if quantum field theory was derived before general relativity, what would have happened was that we would have started with linearized diff invariance. So the symmetry, the underlying symmetry to start with would be linearized diff. So for the spin-2 field to be consistent at the linear level, we need a symmetry which is linear diff, linear diffeomorphism invariance, which is H mu nu goes to H mu nu plus D mu psi nu. And then there's no notion of metric, there's no notion of anything. All we have is flat spacetime, and that a tensor field living on flat spacetime as the representation of a field, a spin-2 field, a representation of Poincare invariance. But we know that if we want now this spin-2 field to interact either with itself or with anyone else at all, then we automatically need the symmetry to be promoted to something which is nonlinear. And now, for those of you who are more math-oriented, which is not my case, so you may know that much better than I do, but the only two group representation that extend linear diff non-linearly, there's only two groups. One of them is linear diff itself. So in principle, I can be stubborn and say, I'm gonna keep linear diff completely non-linearly. The linear diff is what is true, even if I consider non-linear interactions. But we know that this does not work out for us for interacting spin-2 field. So this is only the case for non-interacting spin-2. So if you just had a spin-2 living by itself in flat space, and not communicating with anyone else, that's what you can have. That's fine, but you can never probe it. You can never interact with it. You can never communicate with it. You can never test it. So that it doesn't even couple to a curse metric. It's just on flat spacetime. So this is not gravity. And the only other possibility is to have, well, the name is not very exciting, but let me call it non-linear diff. And that's the other possibility. But perhaps you know a better name for non-linear diff. We can call that as well full covariance or full coordinate transformation invariance. So rather than considering Poincaré transformation on flat space, we can consider a full coordinate transformation. X mu is a function of the all coordinates. And then we see that just considering at the linear level, something like if x tilde mu of x is x mu plus xi mu, maybe I may put a small epsilon xi mu with epsilon being small, if this, if there's such assumption, then we know that we recover the symmetry h mu nu plus epsilon d mu xi nu. But typically, if epsilon is not small, then this is the symmetry. And really what we have is the full coordinate transformation invariance into a much more fledged object, which is the metric, which is g mu nu is eta mu nu plus h mu nu over m Planck. And g mu nu now transforms as an tensor field rank 2 object under full coordinate transformation invariance. And when I write that down, I make no assumption in h mu nu being small or m Planck be large. But it's true that if I want to write it down as a perturbative expansion, then that has to be the case. And so what we see in here, and again, I write it like this because I think this is more fundamental. And if you want to work your way from the bottom up, this is actually what comes in. We just have fields in flat space. And if I want my spin-2 field to be interacting with someone, then what I end up having is that it has to be endowed with a particular symmetry, which is full coordinate transformation invariance. There's no choice. These are the only two possible symmetries that non-linearly represent linear diff. And then we know that we need to have a non-linear representation. So this is the only choice that we have. That's just a pure mathematical group theory statements. And so we know now that if we have a theory which has to satisfy this full coordinate transformation invariance to satisfy stability, to promote linear diff to a nonlinear one, then we will end up with a theory of the spin-2 being something that is embedded in an object, a more fully fledged object, which we can call the metric, and that metric will have to come into an action in a way that satisfies full coordinate transformation invariance. And we know that the only solution in this case is general relativity. So general relativity does emerge completely directly as the unique non-linear implementation of an interacting local Lorentz invariance unitary massless spin-2 field. So understanding that GR is in fact the only representation of an interacting massless spin-2 field is something that has been understood in the 60s and 70s by Weinberg, Deser, Feynman, etc. And it's really, you can think of general relativity as a quantum field theory, and it's a unique quantum field theory for a massless spin-2 field. Yes. So let me just go through I think what you know. But if we add the restriction of the action only contains at most two derivatives, then we know that the unique possibility is general relativity. And so the only thing that we can write down, if I want to interaction between my spin-2, h mu nu, and a scalar field, is exactly as you were saying before. I need to start adding something which is fully covariant, so the square root of the determinant comes in here, and then the promotion of the linearized kinetic term, the Einstein-Hilbert term, to a fully nonlinear one, which is a scalar, now not just under linear diff, but under full nonlinear diff, so under full covariant transformation invariance is a scalar curvature. And then we have minus a half. The kinetic term for the scalar field is also promoted to something that carries fully nonlinear interactions with the metric. So this inverse G mu nu here, and square root minus G mu nu there, and then the potential for the scalar field. So this is the full nonlinear promotion of the action we had before, where we have an infinite number of nonlinear interactions between H mu nu in here and the scalar field in there. We can see that by writing down that the metric G mu nu is equal to eta mu nu plus H mu nu of M Planck. And then when I do this, I can expand this to all orders in powers of H of M Planck. And you'll see that the first term in here is the Lipschitz operator. At 0th order term in here is the free scalar field Lagrangian we had before. And then we start having interaction which goes like H over M Planck times T mu nu of the scalar field, but also an infinite number of higher powers of H of M Planck times derivatives of scalar field and the potential. But in this representation, when we sum everything, we don't need to assume that H of M Planck is small, and we never need it to assume anything at all about that. And now we see that the linearized gauge invariance extends fully nonlinearly to the coordinate transformation invariance, so the linearized gauge symmetry, which we had before as H mu nu goes to H mu nu plus d mu psi nu, that extends to something that carries an infinite number of powers of H over M Planck. So this is what we call that covariance, or what you probably know as the coordinate transformation invariance. So rather than saying something directly about H, what we do is say something about the metric, and that's mu nu plus d mu